We know that electrostatic potential energy, U, for a system of three charges, Q1, Q2, and Q3, can be calculated using the formula U is equal to 1 by 4 pi epsilon naught into Q1 Q2 by R12 plus Q2 Q3 by R23 plus Q3 Q1 by R13, where R12 is the separation between Q1 and Q2. R23 is the separation between Q2 and Q3. And R13 is the separation between Q1 and Q3 respectively. Let this be equation 1. Equation 1 can also be written as U is equal to U12 plus U23 plus U13. Let this be equation 2. In equation 2, U12, U23 and U13 are the electrostatic potential energies for the pairs of charges Q1, Q2, Q2, Q3 and Q1, Q3 respectively. Let us now derive an expression for the electrostatic potential energy of the system of charges in terms of the potentials. Let V be the potential at a point P1 in the electric field E produced by a source charge. Here, R1 is the position vector of the point with respect to the origin. Let us consider a charge Q1 at infinity from point P1. If W1 is the work done to bring the charge Q1 from infinity to the point P1 in the external field, then the external electric potential at the point P1 is V of R1 equal to W1 by Q1. This implies that W1 equal to Q1 into V of R1. Here, we assume that the potential due to the source charge at infinity is 0. This implies that V of R1 is also the potential difference between the point and infinity, which is delta V. Now, if Q1 is released at point P1, it moves away in the direction of the electric field to infinity and gains kinetic energy equal to W1 when it reaches infinity. If V of R1 is plus 1 volt, then the potential difference between the point P1 and infinity is delta V equal to V of R1 minus V infinity, which is equal to plus 1 volt. Now, if Q0 is an electron which is at rest at infinity, is released under a potential difference, then it moves towards the point P1. Since P1 is at higher potential compared to the point at infinity, the electron gains kinetic energy, which is equal to Q0 into V of R1. The magnitude of the charge on the electron is 1.6 into 10 power minus 19 coulomb, and V of R1 is equal to 1 volt. Therefore, the kinetic energy gained will be equal to 1.6 into 10 power minus 19 joule. This kinetic energy gained by the electron is called 1 electron volt. Electron volt is defined as the kinetic energy gained by an electron when accelerated under a potential difference of 1 volt. We have seen that the work done to bring a charge Q1 from infinity to point P1 is given by W1 is equal to Q1 into V of R1. Now let us consider another point P2 in the electric field, whose position vector with respect to the origin is R2. And the external potential at the point is V of R2. Let the distance between points P1 and P2 be R12. Let us bring another charge, Q2, from infinity to the point P2 in the electric field. And let the work done in this process be W2. Hence, work done to move the charge Q2 from infinity to the point P2 is Q2 into V of R2. If Q2 is now released, it moves due to electric field E and also due to the electric field of Q1. Work has to be done to hold the charge Q2 against the force due to the electric field E and also due to that of Q1. Work done to hold Q2 against the electric field due to Q1 is expressed as W12, which is equal to 1 by 4 pi epsilon naught into Q1 Q2 by R12. The total work done to hold Q2 at rest at P2 is Q2 into V of R2 plus W12. Substituting the relation for W12, we have total work done is equal to Q2 into V of R2 plus 1 by 4 pi epsilon naught Q1 Q2 by R12. The total work done to assemble the system of charges in the external electric field is equal to Q1 into V of R1 plus Q2 into V of R2 plus 1 by 4 pi epsilon naught into Q1 Q2 by R12. This is stored as electrostatic potential energy in the system of charges. Let this be equation 3. Now, let us derive an expression for the electrostatic potential energy of an electric dipole in a uniform external electric field of strength E. Consider an electric dipole placed in a uniform electric field of strength E directed along the positive x-axis. The axis of the dipole makes an angle theta with the direction of the electric field. The dipole has charges plus q and minus q separated by distance 2a. Hence, its electric dipole moment P is equal to 2aq. The dipole, when placed in a uniform electric field, experiences a torque tau, which is equal to P cross E equal to P sin theta. Let this be equation 4. This torque rotates the dipole until it is aligned in the direction of the external electric field. Let us apply an external torque tau external equal and opposite to the torque tau, which rotates the dipole from the angle θ1 to the angle θ2, with the field direction without giving the dipole any angular acceleration. That is, at an infinitesimally low angular speed. Let the work done by the external torque in this process be W. Then, W is equal to integral tau external dot d theta in the limits θ1 to θ2. As tau external is equal to tau, we can write W is equal to tau into d theta in the limits θ1 to θ2. Substituting tau equal to P into E sin theta, we get W is equal to integral P E sin theta d theta in the limits θ1 to θ2. Since P and E are constant, we keep them out of the integration, and thereby, carrying out the integration, we get W is equal to minus PE into cos theta 2 minus cos theta 1. This work done by the external torque gets stored as potential energy U in the system in the external electric field. If theta 1 is equal to 90 degrees and if theta 2 equal to theta, then the potential energy in terms of the angle the dipole makes with the external field is U is equal to minus P into E cos theta. We can express PE cos theta as P dot E. Then, potential energy U of the dipole is expressed as U equal to minus P dot E. If V of R1 and V of R2 denote the potentials at the positions of the charges plus Q and minus Q of the electric dipole respectively, the axis of the dipole makes an angle theta with the direction of the electric field, and the distance between the charges R12 equal to 2a. Then, substituting Q1 equal to plus Q and Q2 equals to minus Q in equation 3. And simplifying, we get potential energy U of the system as U is equal to plus Q into V of R1 plus minus Q into V of R2 plus 1 by 4 pi epsilon naught into minus Q square by 2a. This equation can be further simplified as U is equal to Q into V of R1 minus V of R2 minus 1 by 4 pi epsilon naught into Q square by 2a. We can further simplify VR1 minus VR2 as follows. V of R1 will be less than V of R2, since potential decreases in the direction of the field. We can say dV is equal to V of R1 minus V of R2, which is equal to minus EdR. Since dV is equal to minus EdR, from the figure, dr is equal to 2a cos theta. Therefore, V of R1 minus V of R2 will be equal to minus 2a cos theta into E. Multiplying both sides with Q, we get Q into V of R1 minus V of R2 equal to minus Q into 2a cos theta into E. Hence, Q into V of R1 minus V of R2 can be written as minus 2aq cos theta into E. And since dipole moment P equal to 2aq, this can be written as minus PE cos theta. Now the electrostatic potential energy of the system can be written as minus PE cos theta minus 1 by 4 pi epsilon naught Q square by 2a. If the electric dipole were perpendicular to the field direction, then the potential V of R1 will be equal to V of R2, and hence PE cos theta will be equal to 0. And hence, the electrostatic potential energy of the system will be equal to minus 1 by 4 pi epsilon naught Q square by 2a.